Welcome to our MQP project, Opportunistic Communication with Zero and Low Power Radios. To give you a little bit of background, we are trying to develop a zero-power passive radio known as a backscatter. Backscatter radios use ambient RF signals to power themselves and encode information into them for over-the-air transmission. Backscatter radios will be important as within the coming years our Internet of Things, otherwise known as IoT devices, will continue to increase tenfold. As these devices increase, there will be an increased demand for transferring data from end devices to cloud servers for data processing. Since IoT devices are created to be used in a variety of environments, they transmit their data wirelessly through active radios, which use oscillators to mix signals up to a set carrier frequency. However, a byproduct of using active radios is greater power consumption, which leads to higher energy demands. As time progresses, more and more IoT devices will be made and external power supply demand with it. This demand will eventually hit a tipping point and become unsustainable. Implementing methods such as passive backscatter will allow for our IoT devices to continue growing, but with lower energy consumption costs. Our objectives for this project are to design and develop a passive backscatter radio, develop the embedded system to support sending data using the backscatter radio, and to create a breadboard demonstration transmitting from an embedded system.
For the first objective, we designed a backscatter radio. As seen here in the circuit design, our backscatter radio has three main parts. The first part, the Colpitts oscillator, is a low-powered oscillator that oscillates at 200 kilohertz. This oscillator has two parts that makes it low-powered. The first part, 0 VTH MOSFET, has low power consumption. The second part, which is the two capacitors as seen as C1 and C2, have chosen capacitances which allow for a set amount of energy to be fed back into the circuit. Our current configuration allows for 57% energy to be fed back into the circuit, which also creates the oscillation and contributes to even lower power consumption. The second part of the circuit, the switching circuit for the MSP430, is mainly a JFET, which allows the MSP430 to control whether or not the RF energy coming from the oscillator at 200 kilohertz is fed through the antenna, which is the third part of the circuit, or sent to ground. The third part of the circuit, the antenna, is an antenna chosen that will accept energy at a designated carrier frequency. For our application, we chose an antenna tuned to 915 megahertz, which allows energy from 915 megahertz to flow into the backscatter circuit and allows for the RF energy to be mixed up to 915 megahertz coming from the oscillator. These three components together allow for a circuit which can encode information via frequency shifts. The way we use frequency shift keying to encode our information is through shifting energy from the 915 megahertz band of the electromagnetic spectrum 200 kilohertz over using the oscillator. We do a sort of on and off keying in which energy appears and disappears at the 915.2 megahertz part of the spectrum, and we assign a set data rate. This data rate is the set number of bits that would be transmitted within a second. Part of the second part of our project was developing the test bed. Developing the test bed involved several components. The first part, which acts as a prerequisite, is having our backscatter circuit functioning. The second part of the project is configuring an MSP430 microcontroller to encode information from binary numbers stored on device to actual signals that will go over the air. The microcontroller, as seen on the test bed as around the number 4, mainly used its DAC in order to encode information. The DAC would power on and off in a square wave-like fashion, which allowed for ones and zeros to be transmitted through the backscatter circuit, denoted as 3. The two SDRs, 1 and 2, have two different functions. The first one, the receiving SDR, has the main task of recording the information in the electromagnetic spectrum around 915.2 megahertz. The second SDR, the transmitting SDR, supplies energy within the spectrum at 915 megahertz through a constant tone signal. This tone signal would be fed into the backscatter circuit through the antenna, acting as the energy source for the modulation to occur. The fifth part, the oscilloscope, helps us debug the entire setup. The oscilloscope shows the signal coming from the microcontroller at baseband frequency. This allows us to observe the signal coming out of the microcontroller and that is mixed with the oscillator in real time. Through this testbed, we were able to evaluate the performance of our entire backscatter circuit, and we were capable of conducting experiments that needed in order to determine its performance metrics.
We configured our microcontroller to send information in 4 different modes with the click of one of the 4 buttons on the board. Pressing the first button would send the number 1 in 8 bits, pressing the second would send the number 3, and pressing the third would send the number 9, as can be seen in the first 3 oscilloscope graphs. In the final oscilloscope graph, we see when the 4th button is pressed, enabling burst mode, which sends varying 16-bit numbers, simulating real-world use, where multiple pieces of information is sent at once. To test signal power and range of our design, we used the following for our experiment setup. In both setups, we used the same testbed, with the only difference being the box in between our receiving and transmitting SGRs for the non-line of sight test, and then vary the distance of the receiving SGR from the antenna. To test RF energy, we swapped the places of the receiving and transmitting SGRs and measured the signal strength at varying distances. For our results, we found our design to be capable of decoding signals with a signal power of at least negative 77 decibels relative to full scale. We also found the signal range increases as ambient RF energy increases. For voltage, current, and power consumption, we found our transmitter was able to operate at as little as 300 millivolts and 0.6408 microamps and consumes 0.128 microwatt. For decoding information, we found our transmitter to support data rates up to 1,000 bits per second, mostly due to limitations of our microcontroller.